So far, we have discussed a couple of examples of solving the Schrodinger equation in different potentials. So, we have discussed one Schrodinger equation in 1D. Then we have also discussed free particles, and this was related to metals. We have also discussed Schrodinger equation for spherically symmetric potentials, and this was related to hydrogen atom or hydrogen like ions. And this lecture onward, and this is the final example that we will be doing in this course, we are going to focus on electrons or particles in a periodic potential, and again we will restrict ourselves to one dimensional cases, and that is sufficient to give you an idea how bands arise, and this would be related to solids. In general, metals are also like this, and in particular semiconductors and insulators can be explained through this electrons being considered in a periodic potential, and what gives rise to is the band theory of solids. So, let us see what is so specific about periodic potentials. So, when I talk about a periodic potential in 1D Vx, this is Vx plus A, where A is the periodicity. Let me explain this by making pictures. So, for example, if I have a potential like this, where I have shown the potential energy along the y axis and x is obviously on the horizontal axis, and let us say this level which I am showing through dotted lines is V equals 0, and the height of the potential which I am showing by the red dotted line is V. Then you see after a certain distance the potential repeats itself. So, this is the period A. So, this potential Vx is equal to V x plus A. This is a very simple example. We can also have, for example, one dimensional atoms separated by equal distances going all the way from minus infinity to infinity. So, these are the atoms which are shown by green dots in 1D, and each one has its own potential. So, let me make that potential like this. Let us say for proper description I make it finite at the position of the one dimensional atom, and this repeats, is the same everywhere. So, finally, when I add all these potentials, what I get is a potential like I am showing in green out here like this, and it has a period of the distance between the atoms. So, this is also a periodic potential, and we want to solve the Schrodinger equation in this. The periodicity of the potential makes the solution simple, as well as it gives me a new quantum number k. Recall that for free electrons I had the solution e raised to I k x, where k was related to momentum. Here also I am going to have a quantum number k, but please do not go by the similarity in the notation. K does not represent the momentum in this case, as we will see. So, whenever there is a symmetry, so in this potential, let me make it like this. The symmetry is that if I displace the whole thing by a, that means I shift, suppose this point by a. So, this thing looks like this. You cannot really distinguish the shifted system from the original system, right. So, V, this is V x plus a, and the red one is V x. This is a symmetry. Recall earlier we had encountered a symmetry in the cases where V x was equal to V minus x, and in that case we showed that the wave function psi x was either even or odd function of x. So, symmetry led to this property of the wave function. Similarly, this symmetry out here, that the system looks exactly the same when we shift it by a, or the periodicity, is going to lead to certain property of the wave function, which is described by a theorem called Bloch's theorem. To motivate Bloch's theorem, let me recall again how did we arrive at this conclusion for the potential which was symmetric about x equals 0. So, in this case the Schrodinger equation is minus h cross square over 2 m d2 psi over dx square plus V x psi x is equal to E psi x. And what we did in that case was we replaced x by minus x. So, we wrote x y equals minus x, and therefore, the equation in terms of minus x became minus h cross square over 2 m d2 psi over dy square plus V minus y psi y equals E psi y, and therefore, the equation became minus h cross square over 2 m d2 psi over dy square plus V minus y is the same as y, Vy psi y equals E psi y. Notice that the two equations are exactly the same. So, they have the same solution, and therefore, at most the solutions could differ by a constant. So, we had psi x equals some constant psi y, or we had psi x equals some constant psi minus x. Since mod psi square remains the same, because the system has remained the same, when I switch or turn it around by pi, c could be either plus 1 or minus 1. That led to the conclusion that the wave function should be either an odd function or an even function. We are going to do now exactly the same thing in this periodic system. So, I am going to now discuss something called Bloch's theorem, in which case V x plus a is the same as V x. So, my Schrodinger equation is minus h cross square over 2 m psi double prime plus V x psi x equals E psi x. Let me write y equals x plus a. Then I have minus h cross square over 2 m d2 psi over dy square, because the derivative would remain the same even if I shift the coordinate by a, plus v y minus a psi y equals E psi y. Now, V y minus a is the same as V y, and therefore, this equation is minus h cross square over 2 m d2 psi over dy square plus V y psi y equals E psi y. Now, these two equations are exactly the same. So, at most I could have is that psi y, which is psi x plus a, would be equal to some constant psi of x. This is the conclusion. Now, I can do it one more time. So, I can now write my original equation was minus h cross square over 2 m d2 psi over dx square plus Vx psi x equals E psi x, and take y to be equal to x plus 2a. So, even if I shift the system by 2a, nothing really changes. So, again I am going to have the equation minus h cross square over 2 m d2 psi over dx square plus v y minus 2a, which is again the same as v y, and sorry, this should be y square psi y equals E psi y. It is exactly the same equation. So, I am going to have psi y equals some C 2, because I have shifted by 2 psi x. So, remember now, if we shift the lattice or the potential by a, I get psi y equals C 1 psi x, and if we shift the lattice by 2a, I get psi y equals C 2 psi x. Now, think of this, that if I shifted lattice one by one, I would have gotten, if 2a shift was done a step at a time, then I would have gotten psi in the second case to be C 1 square psi x, and this implies that C 2 is equal to C 1 square. That is conclusion number 1. Conclusion number 2, the system looks identical after shift by a or 2a or 3a or so on, and therefore, mod of psi square remains unchanged. Probability of finding a particle at a particular point should remain unchanged if I shift the system, because it is an infinite system, and therefore, mod C square, whether it is C 1 or C 2 or C 3, is equal to 1. So, I have C 2, which is represented, let us say, by C 2a, shift by 2a, is equal to C a C a, and modulus of each is the same, and therefore, the only choice I have is write C as some e raised to I k a, C 1, which is C a, as satisfies both the properties, and therefore, I am going to have psi, if I shift by a, is going to be equal to e raised to I k a psi of x. For a wave function in a potential energy V x equals V x plus a. So, if a particle is moving in a periodic potential, this is the property that it is going to satisfy. So, let us write this Bloch's theorem. For a particle moving in a potential energy which is periodic with period A, the wave function is such that psi x plus a is equal to e raised to I k a psi x. That is the Bloch's theorem. Another way of writing the same thing of writing it is that the wave function psi x is equal to e raised to I k x some u k x, where u k is periodic with the same periodicity, is periodic. This automatically satisfies the upper property. How so? So, I am going to have psi x plus a equals e raised to I k x plus a u k x plus a, and since u is periodic, I am going to have this as e raised to I k a e raised to I k x u k x, which is same as e raised to I k a psi. Let me now label it as k x. Let me now label this as k x. So, both are the same properties. So, this is the Bloch's theorem, that the wave function in a periodic potential, this is the Bloch's theorem, that a particle moving in a periodic potential has the form of the wave function, which is given either by this upper box or the lower box. Both are one and the same thing. This leads to interesting properties. Now, when the wave function I am labeling it by k, x is e raised to I k x u k x, right. If v x plus a equals v x is equal to a constant, then I know in that case particle is free and the wave function psi k x is e raised to I k x and u k x, therefore, in that case is 1. So, as the potential is increased, it becomes non-constant, but remains periodic, you get this u k, which is different from that constant or 1. In the second case, k represents the momentum of the particle. How so? Because if I take p operator operating on e raised to I k x, I get h cross k e raised to I k x. So, this is a momentum eigenstate, as we have said again and again while discussing these things earlier. On the other hand, if psi k x equals e raised to I k x u k x, then k does not give the momentum of the particle, because this is not an eigenstate of the momentum. So, there is the momentum is not conserved. That is also quite easy to see. If I do p psi k x, this is equal to h cross over I d by dx of e raised to I k x u k x, and this is certainly not equal to some constant times e raised to I k x u k x. This is not equal to that. So, there is no conservation of momentum. So, momentum cannot really be defined for these states. Nonetheless, k is a good quantum number, which is related to the symmetry that if you translate the whole system by the period A, nothing changes. Now, when I write psi k x as e raised to I k x u k x, this can also be written as e raised to I k plus some quantity related to the periodicity, and u k plus some quantity related to the periodicity times x, which I am going to explain now. So, when V x plus a is equal to V x, V x can be written in the form using Fourier series summation of n some constant C n times e raised to I 2 pi over a x times n, and these C n's I am going to call the nth component of V. So, I am going to write this as summation n V n e raised to I n 2 pi over a x. V 0 is basically a constant, and V n, V 1, V 2, all these are constants. Now, V 0 has a particular significance, because n equals 0 gives me e raised to I n 2 pi over a x to be equal to 1, and therefore, what V 0 represents is just a reference point for the potential. So, it does not really affect the solution. All this does is changes the reference point for the energy. So, the potential components that affect the solution are the components V 1, V 2 and so on. So, we have V x equals summation n V n e raised to I n 2 pi over a x. I am going to call 2 pi over a as equal to g 1 and n times 2 pi over a as g n, and these are called as reciprocal, that is vectors, but that is just a name I am giving you. But right now, let us just then therefore write V x equals summation n V n e raised to I g n x. Notice that e raised to I g n times a is equal to 1. That is by Fourier theorem. Therefore, V x plus a becomes same as V x. So, g n is 2 pi over a, and that is reciprocal space or reciprocal lattice vectors. Since psi k x is equal to e raised to I k x u k x and u k x is also periodic, I can write u k x also as equal to some u n e raised to I g n x summation over n. So, I have psi k x equals e raised to I k x summation over n u n e raised to I g n x. I could also write this as equal to e raised to I k plus some specific g. Let me call it g 1 x summation n u n e raised to I g n minus g 1 x. I could also write this as e raised to I k plus g 2 x summation over n u n e raised to I g n minus g 2 x. Even if I do so, notice that any e raised to I g n minus g 1 a or e raised to I g n minus g 2 a is 1, and therefore, summation u n e raised to I g n minus g 1 x is also periodic with the same periodicity A. So, I could write psi k x, which is e raised to I k x u k x, also as e raised to I k plus g 1 x u. I will call the function with g 1 as u k plus g 1 x. It is the same, satisfies the Bloch's theorem. I could also write this as e raised to I k plus g 2 x u k plus g 2 x, and therefore, the final solution remains the same, and therefore, what we conclude is that in a periodic potential k, k plus g 1, k plus g 2 and so on are all equivalent. So, I could label the wave function by either k, k plus g 1, k plus g 2, and then we follow a convention that we will restrict k to within certain boundaries. So, what we just seen is that if I have a psi k, which is written as e raised to I k x u k x, I could have written this also as u e raised to I k plus some general reciprocal space vector u k plus g x, and both satisfy the Bloch's theorem. G obviously, as we have been saying, is some n times 2 pi over a. So, k and any k plus g are equivalent as far as the wave function is concerned, and this is because of the periodicity of the wave function and periodicity of the lattice. So, what the convention we follow is restrict k to minus pi by a to plus pi by a. So, just to show it pictorially, if I have k equals 0, pi by a, 2 pi by a and so on, minus pi by a, minus 2 pi by a, then what we have discussed so far is this point at 0, which I am showing by red circle, is equivalent to this point. Point at pi by a is equivalent to minus pi by a and so on, and this 2 pi by a is equivalent to then 4 pi by a and so on. So, what we do is, instead of specifying k over all these, we restrict our k to within this minus pi by a to pi by a, and therefore, then we actually map the entire k space. So, this is known as the first Brillouin zone. So, we work within the first Brillouin zone. I am just giving you these words so that if you hear them, you do not really feel intimidated what it is. All these are equivalent, so I can restrict myself to working within k within minus pi by a to pi by a. Now, write the solution, because we wrote psi k equals e raised to I k x u k x, and since u k is periodic, we wrote this as e raised to I k x summation u n e raised to I g n x, which I can write as summation u n e raised to I k plus g n x. Just for the convention's sake, let me write this u n as c n, some coefficient c n. So, I am writing my psi k x equals summation n c n e raised to I k plus g n x. This is another way I can write the wave function, and you see this wave function carries all momenta k, k plus g 1, k plus g 2, k plus g 3 and so on. k minus g1, k minus g2 and so on, and varies from minus infinity to plus infinity. And therefore, it does not really matter whether I specify the wave function by k, k plus g1, k plus g2, k plus g3. It is another way of seeing that all these are equivalent. If they are all equivalent, again I will restrict myself to k being between minus g1 by 2 to g1 by 2 in the first Brillouin zone. Now, once we have this equation, so this is the third way. One can express Bloch's theorem, that is, that psi k x is of the form summation minus infinity to infinity C n e raised to I k plus g n x. And this form is useful in writing the equation for the C n's and then from that getting the band structure. That is why I introduced this. So, I will just conclude this introduction to Bloch's theorem. So, conclusion: when a particle is moving in a periodic potential, V x equals V x plus a is equal to V x plus 2a and so on, its wave function satisfies the Bloch's theorem. What is Bloch's theorem? So, psi x is such that psi x plus a is equal to e raised to I k a psi x, and we label this by k. This can be expressed in another form, that psi x, again I will label it as k, is equal to e raised to I k x u k x, where u is also periodic, u k a plus x. And finally, I can also write this as psi k x equals summation n equals minus infinity to infinity C n e raised to I k plus g n x.